The next section is about roots of complex numbers. Let's consider a non-zero complex number set represented by this point in the complex plane. The fact that this is non-zero is clear from the figure because it's not the origin. As a point, it's not coinciding with the origin. Its distance from the origin is, say, r, some positive real number which equals the absolute value of the complex number. So that means this is the magnitude of this radius vector, and theta is some argument of the complex number. And here in this figure, theta is this angle between this radius vector and the positive real axis. Now it's of course clear from the figure that if theta is increased or decreased by 2 pi, then we end up at the same location, at the same point. What does it mean for theta to be increased by 2 pi? If you increase theta by 2 pi, then the point rotates on the circle anticlockwise through an angle 2 pi. So it comes back to the original location, and decreasing theta by 2 pi, in other words, adding minus 2 pi to theta corresponds to a clockwise rotation, one complete revolution in the clockwise sense. So we come back at the same location, and that's why we have this. Say you have two non-zero complex numbers z1 and z2 whose exponential forms are given. r1 times exponent of I theta 1, and for this one r2 times exponent of I theta 2. Then they are equal if and only if r1 equals r2 and theta 1 equals theta 2 plus some integer multiple of 2 pi, where k is some integer. And the figure that you saw just now here, which you don't see anymore, that makes it clear why we have this. Two such complex numbers are represented by points in the complex plane. So if they have to be equal, they should be first of all at the same distance from the origin. That's why we have these two. And why the arguments are related like this, that becomes clear from the way we saw the rotation. Now consider a non-zero complex number z0 whose exponential form is given, r0 times exponent of I theta 0. Let n be an integer which is at least 2. We call a complex number z an nth root of that z0 if this happens, if the nth power of z equals z0. Now we will try to find all such nth roots of a given non-zero complex number z0. Now the first thing you note here about such a complex number z is that it needs to be non-zero. Why? Because if z is 0 and still this equation is true, then z0 becomes 0, but z0 is given to be non-zero. That's why. Now because z is non-zero, we can write z like this. It will have some exponential form, and I say some because although this r is fixed for that z, it is its absolute value, but this theta you can change. There are infinitely many possible arguments. So now we consider the equation itself. If z is a complex number whose nth power equals z0, then this equation is of course equivalent to this. Here we have written the exponential forms of z and z0. Alright. Now from what we saw in the previous video, this n gets distributed over this product. It comes over this r, and also with this it gets multiplied. Multiplied means the argument gets multiplied. So here the argument is theta, it becomes n theta. Alright. Now you look at this equation. Here it's a non-zero complex number. This one is also a non-zero complex number. And just now we saw that two such non-zero complex numbers are equal if and only if their absolute values are equal and their arguments differ by some integer multiple of 2 pi. So that's how we are having this. And from this, of course, you have your usual real analysis thing. R0 is a positive real number. Why is R0 positive? In general, R0 being absolute value will be non-negative. Because R0 is the absolute value of z0 which is a non-zero complex number. So that's why r0 is positive. And from real analysis we know that any such positive real number has a unique positive nth root. So it's that thing, it's coming from real analysis. And from this second equation, of course, you can find theta in a very simple way. You divide both sides by n and have theta to be this, where k is some integer. Okay, so this is where we are right now. Z is a complex number satisfying this equation if and only if we have these things. In other words, z is an nth root of z0 if and only if these things happen. And we can of course continue with one more step. Instead of stopping here itself, we can write what z is. That is, we can write the exponential form of z. This is the magnitude, the absolute value of z, and these are the possible arguments of z. So obviously the exponential form will be this: absolute value times exponent of I times all possible arguments, where k is any integer. Now from this exponential form, it seems at once that there will be infinitely many nth roots because of this part. The set of integers is infinite. Are we going to get infinitely many distinct roots as k varies over this set? No. To understand why, the best way is to look at the geometry, what's going on geometrically. From the above exponential form, we see that all the nth roots lie on this circle. The circle centered at the origin and having this radius. That's obvious. If you take absolute value on both sides, on this side the absolute value of this is itself, because it's a positive real number, and the absolute value of this type of complex numbers is 1. We have already seen that. So that's why geometrically all the nth roots will lie on this circle, and additionally, because of how these arguments are, they will be equally spaced every 2 pi divided by n radian, starting with this argument. What this means is that, say you want to locate an nth root, say that nth root which corresponds to this argument. What do? First you draw this circle in the complex plane, whose center is the origin and whose radius is this positive real number. Okay. And then on the circle, you locate that point whose argument is this. So that will be one nth root. Let's give it a name. So we call it C0. Okay, C suffix 0. And then what you do, from C0, you go through a rotation in the anticlockwise direction by this angle 2 pi divided by n radian. So you will then land at another location. That will be another nth root, and you repeat this process. From that new nth root, if we call it C1, you get to C2 via another such anticlockwise rotation through this angle. So that way you continue getting distinct nth roots, but of course this process will not let you get infinitely many distinct nth roots, because by the time you repeat this process n times, you have rotated through an angle 2 pi radian in the anticlockwise direction. So that means you have come back to that location, the location of C0. And this tells you that there will be precisely n distinct nth roots, not more than that, nor less than that. So the distinct nth roots are these. Precisely n of them are there. To show the dependence of this root on this k, we have written ck, and k varies like this from 0 to n minus 1. If you want, you can vary k differently also. Say you want to start from 1 instead of 0, but then you have to go till n in order to capture all the roots. A different set of k values won't really give you different roots, but it will give you those same roots slightly differently in a different order. Suppose we consider a positive real number z0. Okay, that's one candidate for z0. Then if our n is 2, I forgot to write that here, but if n is 2, then we are seeking square roots of z0. Because of this observation, there will be precisely 2 square roots. One of them is c0, which from this formula becomes what? So this is the square root of z0 in the sense of real analysis. We know that it exists and it's also a positive real number times exponent of I times 2k pi divided by n. K here is 0 and n here is 2. But anyway, because of this 0, it becomes exponent of I0, or what is it actually? It is cos 0 plus I sin 0. It is 1 after all. So we get this 1 square root, which is your familiar square root that also lies on the real line on the right side of the origin. It's a positive real number, just like z0. And this is the other square root, c1. c1 again is just like this. The only difference is that here in place of k you have 1. So now this does not vanish, it does not become 0, it becomes I pi after doing the cancellation. What is exponent of I pi? Cos pi plus I sin pi. Sin pi is 0, cos pi is minus 1. So you get minus square root of z0. So this is your other square root that also you know from real analysis it exists. What are these numbers? These are the only numbers whose squares equal z0. And because the nth roots are equally spaced on the circle, so when n is at least 3, they lie at the vertices of a regular polygon with n sides, which is inscribed in this circle. For example, if n is equal to 3 and say z0 is some non-zero complex number, then the 3 cube roots of z0 will lie at the vertices of some equilateral triangle which is inscribed in this circle. We shall denote the set of all nth roots of z0 by this notation, z0 to the power 1 divided by n. Okay, so this is not a single complex number but rather a set of complex numbers. If you want to view it as a function, then it's not a traditional function but a multi-valued function. And we reserve this symbol to mean the positive nth root of a positive real number z0 that comes from real analysis. Now you may or may not have noticed in our calculation this fact that the argument theta 0 or z0 which we had from the beginning, it may be any argument of z0. z0 has infinitely many arguments, but of course it has one principal argument. If your theta 0 is that principal argument, then the nth root c0 is called the principal root of z0 or the principal nth root. For example, if your complex number is a positive real number, then what is its principal argument? 0. So that is why c0, which is this and which corresponds to that principal argument, is the principal root or principal nth root of z0. Next we have section 9, which has examples. Don't be afraid, it won't take long, there are only 3 examples. In example 1, we try to find the nth roots of 1, nth roots of unity. So what we do, we write the number 1 in exponential form, but using all possible arguments. There is an advantage of doing this, you will see. So 1 is of course equal to 1 because 1 is the absolute value of itself times exponent of I times 0. 0 is one argument plus, in fact 0 is the principal argument because this is a positive real number, plus 2k pi where k is any integer. And the advantage of writing 1 like this in this general fashion is that now you can write the nth roots from this itself. Just you take the real nth root of 1, which is 1 itself. So I have written 1 here. Actually I should have written nth root of 1, but you understand that. And here you just divide this part by n, that's it. So that's why we wrote this part like this, 0 divided by n plus 2k pi divided by n, where k varies like this, you already know. So it reduces to this. So these are the nth roots of 1 of unity. Now suppose you concentrate on the nth root C1, which corresponds to the value k equal to 1, and you give it a new name. So you call it omega n. Then it's not difficult to see from properties of exponential form and their powers that the kth power of this omega n is just this ck. So from this fact we get these nth roots in this new form, and in fact this is more familiar to you. 1 omega n square and so on up to the n minus 1th power of omega n. Usually we don't write this suffix n. If it's understood what n is, we write omega. So there you get the nth roots like this, 1 omega square all the way up to the n minus 1th power of omega. In example 2, we considered the purely imaginary number minus 8i. So geometrically it lies on the negative imaginary axis, 8 units distance away from the origin. And its exponential form can be written like this. The absolute value of course is 8 times exponent of I times. So you need to write an argument here. So why not the principal argument? The principal argument for this type of numbers is of course minus pi divided by 2. So that we have written plus 2k pi as usual, where k is some integer. Now we want to find the cube roots of minus 8i. So there will be 3 cube roots. So the cube roots of course are these, ck, where ck is, this is the real cube root of 8. In its place you have to write 2. I did not write one more line for that, okay. And what will you do in this part? In this part you divide this part within parenthesis by 3, that's it. Minus pi divided by 6 plus 2k pi divided by 3. And k takes on these values 0, 1 and 2. You can do one thing with this example. Actually in the book it's given in a more detailed manner. You find out these complex numbers in their standard form. That is one thing. And the second thing is you then take their cubes and see if you get minus 8i. And finally we have example 3, where our complex number is square root of 3 plus I, whose absolute value is 2, magnitude is 2. And you can easily find it. Its principal argument is pi divided by 6. So this is exponential form. So this time we seek the square roots of this number. So there will be 2 and they are these ck's. So what will you do here with this formula? You take the real square root of 2 and you divide this part by 2. That's it. So this becomes pi divided by 12 plus k pi. Here k takes on these two values only, 0 and 1, because our n is 2. There is one more section, and that's on the topology of the complex plane. I initially thought that in this video itself I could do it, but now it has already become quite long, I think. So if I include topology also, then it will become exceedingly long. So we will see that in the next complex analysis video, and then this chapter will be over.